Hi everyone, I think we're now live here at Sands Films in Rotherhithe. I want to welcome everyone to this evening. My name is Jo Weir and I'm going to be one of two people in the audience here. The other person is Ala Katab, who is sitting in the audience there, and I'll be joining him. I'm sorry more people can't be in the audience, but we're really pleased that people can join us from around the world actually tonight. So we want to thank, this lecture has been organized by Bermondsey Welcomes Refugees, and we want to welcome all of you to that, and we want to thank everyone who made a donation. We have a Just Giving page, so if anyone wants to make a donation at the end of the lecture, there will be a link. I also want to thank Sands Films for hosting this event. They've been very generous to us, and I recommend that everyone check out their online events. Without further ado, I'd like to introduce Francisco Diego, who's going to be doing the lecture. Thanks, Francisco.
Thank you very much. It's a pleasure to be here, Joe and Ala. It's a very important event, I think. This kind of fundraising is extremely important given the situation in the world. I'm very delighted and honored to be here and to deliver this talk about one of my favorite topics actually is very close to my heart, which is life in the universe. How did it all start? How did it develop? And how we have this amazing paradise that we have now here, but will it happen elsewhere? So at the end of this talk, that it will be about an hour long, a bit less probably, we will have time to answer some questions. You will have a possibility of sending your questions by the chat in Vimeo. And then we will try to deal with them, not so much answer them. Some of these questions are very important. We cannot answer them. That's the situation. So now my question to you. Do you think that there are aliens? Do you think there is alien intelligence out there? Let's find out. In the beginning, Ra came out of an egg that was floating over the water. And Ra brought forth 4 children, the gods Shu and Geb and the goddesses Tefnut and Nut. Shu and Geb became the atmosphere, and this Tut and Geb became the earth, and the goddess Nut, with her naked body, became the sky. In the beginning, God created the heavens and the earth. And the earth was formless and empty. Darkness was upon the surface of the deep. And the Spirit of God was hovering over the waters. And God said, "Let there be light." And there was light. So here we have a few ideas, a few concepts that try to explain the origin of everything. Of course, they're all myths, they are not true, but in their time, that was what was available. So we have this mystery of the sky over our heads, moving in a very mysterious way, giving the impression that we are at the center of the universe. This was challenged very seriously in the 1500s by Nicholas Copernicus, that came with a new idea that the Earth was just another world similar to the planets as we see in the sky, and his model can be seen here in a computer animation. These ideas were heretic. They were persecuted by the Inquisition in Europe at the time. This is the 1500s. And the ideas of Nicholas Copernicus were persecuted very violently, actually, to the extreme limits in some cases, and his books were banned for hundreds of years. So we have the Dominican monk Giordano Bruno that came after Copernicus towards the end of the 1500s, and he was a defender of the Copernican ideas. This, I must remind you, is before the invention of the telescope. But he came with so much insight, beautiful insight, that is, we could say, well, more kind of the father of science, but more than the father of science, we could regard Giordano Bruno as the father of philosophy. And a lot of philosophers that follow were inspired by Giordano Bruno. Let's listen to Giordano Bruno.
To a body of infinite size, there can be ascribed neither center nor boundary. Thus the earth, no more than any other world, is at the center. It is then unnecessary to investigate whether there be beyond the heaven, space, void, or time. For there is a single general space, a single vast immensity which we may call void. In this void are innumerable globes like this earth on which we live and grow. This space we declare to be infinite, since neither reason, convenience, sense, perception, nor nature assign to it a limit. In it are an infinite number of worlds of the same kind as our own.
For this and other ideas, Giordano Bruno was taken prisoner by the Inquisition, and for 7 years he was tortured, and because he refused to repent, he was tried for heresy and burned alive at the stake in this place, Campo di Fiori, in Rome. Amazing ideas that now resonate, as we will see later on in this talk. Just after that, Galileo comes with the remake of the telescope that had been invented just at that time, but he took the idea and made proper telescopes that can see in detail and pointing them to the sky. Of course, you have telescope. The first thing you do is to point the telescope to the sky. You point the telescope to the moon, and you choose the moon to do that. And then he had amazing conclusions, because this is the telescope giving him the evidence. So you see, it's not smooth or perfectly spherical, as the philosophers wanted to be. But on the other hand, it is completely rough, uneven, and crowded with depressions and bulges. And then he makes the analogy. This is the important thing. It is like the surface of the earth itself. You see, the moon is another world. This is no big idea. This is no big philosophy around here. You take the telescope, you see that. On the left, you have the moon. On the right, you have a landscape seen on our planet. Amazing stuff. So Copernicus was right. Nevertheless, Galileo was taken prisoner by the Inquisition, and in 1633 he was tried for heresy. He accepted to sign a document when he said that what his ideas were not true or something like that, and he was forced to spend the rest of his life in house arrest. His telescope was developed further, a couple of 100 years later or so. This is a lovely telescope that we have in the observatory in Mill Hill in North London. I work for University College London, and we use that telescope quite a lot. It's my favorite telescope, really. This was made in 1842. Amazing, amazing telescope. So telescopes like this were used in the end of the 19th century. This is William Huggins in South London, using his telescope at the time to look at the stars in a different way. You put a prism at the bottom of the telescope, you get the spectra. You see the little colors here of the spectrum of stars, spectra of stars. And again, these are the scientists making these philosophical advances and saying, it is amazing that the chemistry of the universe is the same everywhere. That's what we find. Same chemical elements. And in yellow, you will see, I read it for you. May it not be that at least the brighter stars are like our sun, the upholding and energizing centers of systems of worlds adapted to be the abode of living beings. And look at the date. This date is 1864. This is only 5 years after the origin of species by natural selection, Darwin. So these themes were floating around very, very clearly. So what I'm going to do is to now do a demonstration. So I am going to talk to you about the origin of the universe, which is an event that we know, we call it the Big Bang. And it is a mystery. Still today, the origin of origins, it is a big mystery. So we need to make a leap of faith here in a way to understand what the evidence is telling us about the origin of the universe. And we are going to go from there to life in the universe, to aliens and the rest of it. And I hope to do that in the next few minutes. Now, how does that happen? Well, if I ask you, can you imagine, make a picture of 100 years in your mind? You can picture that? 1,000 years? I can do that. A few thousand years, go back to the pyramids, to Stonehenge. A bit beyond 20,000 years, the paintings in Lascaux and Altamira in Europe. How about 100,000 years? How about 1,000,000 years? I struggle. If you don't, please let me know how you do it. But how about 100 million years? How about 1,000 million years? We are lost. How about 13.8 thousand million years? So in order to visualize that, which is impossible otherwise, we are going to use the timeline. The timeline is a rope that we are going to display here in the theater, where the scale of time is going to be 1 millimeter for every million years. In other words, this will be 100 million years, this will be 500 million years, that sort of thing. So I'm going to come to fix this timeline here in our stage, because we are going to see what happens when along this timeline. So the length of this timeline is about 14 meters, which will be 14,000 million years, which is more or less what we found out is the age of the universe. So at that end over there will be the beginning, will be the origin of the universe, the Big Bang, and all along this time we are going to see what happens until we come to this point, which is today. I'm happy to say that there is plenty of rope that goes thousands of times in the future, so we don't have to worry too much about it. But we know that that timeline will have an end at some point. So I'm going to now to go to the beginning of the timeline. What you have in your screen is a little dot. Well, you see the picture of the universe as it was born. It's the baby universe. So this is the origin of the universe. So I'm going to fix this image here on our timeline at the beginning, time 0. And then that little dot, which was actually much smaller than you see there, it was minute. It didn't have any matter, any particles, any planets or stars or anything that we see today. It was pure energy. Just pure energy. So everything we have today in the universe comes from that energy. Everything. Nothing else has been created, so to speak. The creation is this one, is this Big Bang, which is fascinating, it's amazing. So if we go forward, we see the expansion of the universe that starts to expand. That little dot contains the space itself, and the space starts to inflate like a balloon, and the space starts to inflate very fast and cools down. Remember, there is nothing else to be put in the universe at that point. It starts to cool down, and with the cooling down, it produces this energy is transformed into particles, as we see here on the right, and those particles start to get together to form clusters of particles, and that happens very quickly, in a fraction of a second. And then, after a few minutes, we have this kind of fusion of particles that eventually they are going to produce atoms that we have here. So these atoms that come in the first 300,000 or 400,000 years of the universe, of course this timeline is now, I'm cheating because I'm eating time in the timeline. All these images should be instantaneous here, but just for the sake of the demonstration, we have to do that. So these atoms are going to be the only atoms that appear in the universe. And then the universe keeps expanding and cooling down. When the temperature goes below 50 million degrees, it stops, and then we get atoms like hydrogen, helium, and lithium. And that was the origin of the universe. So the expansion continues, the cooling down continues, and that process has to stop, and the universe comes to a dark part, the dark universe. So the dark universe is a cloud of hydrogen and helium mainly that is expanding forever, cooling down, getting darker and darker. So that was the beginning of the universe. Amazing. And that darkness lasted for 400 million years. So after that darkness, what we get here is the formation of the very first stars in the universe. So we see here that these clouds are collapsing and producing the first stars made out of hydrogen and helium. And the stars are very important because, as we see in the next image, we see the enormous pressure of the gas, the hydrogen and helium, that is producing enormous pressure and making the temperature in the core very, very high, as you will see in the next picture. So this temperature of 15 million degrees or more comes to the point that the particles can get together as it happened before. When the stars are dying, the core of the star goes higher temperature. We can get larger numbers of these particles together to form the nuclei. This is why it's called nuclear fusion, which are the nuclei that we see here, a bunch of particles in the center of this atom that happens to be carbon, which has 6 protons, 6 neutrons, these particles we were talking about, and 6 electrons around. And this was the chemistry of the universe that was being produced by the stars. So by now you're thinking, so the stars are making this because they are very hot. But these stars not for a very long time, because they will explode, as we see in the next image, which I'm going to fix here in our timeline. So the next a few million years, give or take a few million years, these stars live very short lives and they explode. And during the explosion, in the next slide, we can see that the temperatures in those gases that were part of the star become so hot, thousands of millions of degrees. And at those temperatures, we get the protons and neutrons going together into larger and larger numbers. So here we see in those clouds that were stars, we see the nuclei of heavy atoms like, oxygen, carbon we have there, gold, silicon, uranium. So in a few generations of this process going on when the stars explode and then new stars are formed, we have the formation of the chemical elements, all of them. And when I say all of them, I mean all of them. There are no missing chemical elements in nature that we don't know of. And this is one of the most important things that we have achieved in our exploration of the universe, the development of the periodic table, which is a monument to nature. With the yellow arrows that we see here, you will see the enhanced atoms that are the important ones for life. You see the hydrogen in the top left, then you have carbon, oxygen, nitrogen, oxygen on the right, and then below them, in number 20, we have calcium, which is especially valuable for vertebrates like dinosaurs and people. So all those come from the stars that were living so long ago. So now in the next image, we see those clouds expanding and waiting to collapse again to produce new generations of stars. And then we see here in some clouds of these gases that are collapsing and producing new generations of stars. But now we have metals, we have rocks. So now we have the possibilities of producing planets. So the images that we have here, I'm going to fix that image on the timeline, the one you have there, because these were the very first solar systems that came about when the universe was about a third of our present age. So we have solar systems and planets already there. You can see the planets in this image here. So the possibilities of alien life, I have here some aliens that you can see. So we have, because I must say, the process I'm describing is very common in the universe. Now we know that this is the way the planets form and the solar systems form. And this process has been going on for thousands of millions of years, well before our solar system came to be. So the possibilities of aliens started here thousands and thousands of millions of years before our own solar system. So imagine aliens in that time were able to develop all kinds of technologies and populate the universe. We will have evidence for aliens all over the place. Now they have to move very quickly because those stars are going to end their lives in different ways. And in those clouds that you see there surrounding the explosion, you will see the remains of those planets and the remains of those aliens. In fact, let me just fix a few more aliens here because we have aliens all over the place, if that was the case, because who knows? I hope you know where I'm going to with this demonstration. There is a yellow one here. I'm afraid they all have hands and legs and smiles and heads and possibly brains, but I don't imagine aliens otherwise. So we are a bit anthropocentric here, but anyway, so those clouds that were planets and aliens will go into space and will start to collapse again to form new generations of stars and planets. You see, this is a cosmic recycling. You see here some blobs that appear in some of the clouds that we see today. These are the blobs out of which one of those blobs could be one of the ones that form our own solar system. Now, in the next image, we have our own solar system that is forming. If you can see what I'm doing here, this is about 1,000 million years, okay? It's about a meter. 1, 2, 3, 4.5. So it will be 4,566 million years ago. Isn't that amazing? So that's the image that you have there. So that is the formation of our solar system at that time. And now we are going to review what happened since then. I mean, before this, the universe is relatively boring. You are talking about stars, formation of chemical elements, recycling chemical elements, stars die, planets are born. We don't know if there were aliens there. That will make the thing more interesting, but we don't have any evidence. But here we know what happened after this, and this makes the rest of the timeline extremely challenging, extremely beautiful, because this is the evidence that we are going to come from to have biology. I mean, so far we're talking about physics and chemistry, but biology is still to come. So let's have a look at the list of conditions. We have the right star at the right distance, which is very important. We need liquid water on the surface, and we have. So the sun is the right star at the right distance. However, that place was extremely violent. You see collisions like this one, and in the next image we have an animation that shows the collision of two planets, really. On the left is the Earth, and on the right is a planet the size of Mars called Theia. According to this animation, it was missing, almost missing the Earth, but collided, and that collision was extremely important. It had several consequences. The most important one from our point of view is the formation of the moon. Of course, the leftover material that we see here still in orbit around the Earth is the moon, eventually forming, but also the internal structure of the Earth will change. We have a magnetic field. We are going to see all that in a minute. The spin of the Earth also was changed, and the axis of the Earth was tilted. So these collisions, we have several artistic representations, but I have to emphasize, they are by accident. They are by accident. So we keep going with these conditions. There are more, and then you will see how difficult it is to put all this together to form a planet that will host intelligent life. So here we see the primeval Earth, the primeval moon, the tilt of the axis of the Earth, and the moon going around the Earth, keeping that tilt constant, which is very important for the future development. The bombardment continues with asteroids and comets that are bringing to the Earth a lot of water that is accumulating in our oceans. So that water was very important because something was going to happen on the surface of the planet. We have the liquid water, we have the chemistry, that will be based in the atom of carbon that I mentioned before, number 6. And this atom will have the ability to combine with other atoms. In the gray we see carbon, the blue is nitrogen, the white is hydrogen, and the red is oxygen. So these atoms, when they combine, they form molecules, which are very important, very simple molecules that we see here. On the top left, we see carbon monoxide. We see water in the center, and then ammonia with the nitrogen in the middle, methane, carbon dioxide, etc. So all these very fundamental molecules are going to be very important in that primeval Earth, which was really, I would say, in the beginning, the Earth was hell, because it was bombarded by meteorites, by asteroids, by comets, and they have a simultaneous volcanic eruption, throwing all kinds of nasty greenhouse gases into the atmospheres, and also enormous magnetic storms and electric storms. So we go down inside the Earth as a consequence of that collision with Theia. We see the structure of the Earth that has different cores. The red part is the mantle, which is semi-molten, and the mantle has the eruption that happens in the middle of the ocean. And in the middle of the ocean, we have submarine volcanic eruptions that we have discovered only recently when we have the technology to reach these places. And it is in these places that the chemistry may have, in those times, achieved the levels of complexity that life requires. We have images taken by submarines now. So this is the kind of chemistry we are talking about. And that chemistry eventually comes into a very complex, well, they're not that complex because they only have 5 atoms. The 4 we mentioned, carbon, oxygen, nitrogen, and hydrogen, but also we have phosphorus, which is the yellow bit here, and this is the DNA, which is the molecule that every single living thing that has ever been on this planet and in the future will have that molecule in every single cell. That is an amazing discovery that we have today. The cell has the ability to reproduce itself, and sometimes it does very well, sometimes there are mutations, there are mistakes, but that makes life interesting because then we are going to see the diversity that comes from that. So what I'm doing now here on the timeline is to fix, because this, I have to say, happens very quickly in the formation of the solar system. We have the Earth already there, and the formation of DNA happens in the first few 100 million years, very quickly really, until we have that DNA encapsulated in membranes to form the very first cells that we see in the next image, which are the bacteria that we still have today. So these bacteria, we have evidence for them in rocks which are nearly 4,000 million years old here on Earth. Some of them are able to photosynthesize. Remember, the Earth as it was, the hell that was there full of greenhouse gases, was going to be changing because of this. Some of these bacteria, the cyanobacteria, the blue-green algae, which have the ability of photosynthesis. In the next image, we see the image of the slime that we still see in our beaches. And those green algae were able to photosynthesize, to wipe out the carbon dioxide from the atmosphere, release the oxygen, and then change the balance of the atmosphere, which was carbon dioxide rich, and now is going to be oxygen richer, which means that the greenhouse effect is mitigated and the Earth cools down just in time to have an atmosphere that preserves the liquid water. So that hell that was there in the beginning, thanks to the photosynthetic action of bacteria, became a paradise. But that paradise took about 2,000 million years to happen. So I have to move 2 meters along our timeline. So we have to thank the very patient and perseverance action of cyanobacteria to give us the oxygen that we have today and the cooler atmosphere that we have today. So we go back to our list of conditions. You see, we're accumulating all these conditions that we had before. Now we have photosynthesis. We need an oxygen-rich atmosphere, which is going to be very important for what happens next. Here we have again the internal structure of the Earth, and on the surface we have the process of you see these arrows in the red part, which is the mantle, which is eruptions of semi-molten rock, which is very relatively light rock. But you have the basalt, which is at the bottom of the ocean, which is moving as a conveyor belt. And this is the driving mechanisms that we see here. The number as you see there is millions of years ago. These are the shape of the continents. You can see Antarctica, you can see India there, Madagascar, and you see how they come closer, how they come apart. Now South America and Africa were together about 100 million years ago. They separate, and now is more or less the planet that we have today. Of course, this process continues in the future. That process of plate tectonics is fundamental because that keeps our planet with land masses, with oceans, and with air. The three fundamental environmental conditions that we need for complex life. So let's add that into our list of conditions. You see we are running out of space down there. Plate tectonics, continents, dry land. So another thing that we get from the inside of the Earth is magic. I mean, no other planet has the same thing, which is a molten core of iron, which is electrically charged. And when you have electrically charged materials that are moving, that generates a magnetic field. So the magnetic field of the Earth is extremely important. It has been extremely important along history because it shields us. On the left, we have the sun here sending lethal radiation towards the Earth, which is defending itself with that magnetic field. Without that, we would have lost our atmosphere. The DNA on life would have been completely almost destroyed. So one more thing to put in our we are nearly at the end now in our list of conditions there. So, well, in these conditions now, we have that the bacteria are able to produce kind of colonies. It's a kind of endosymbiosis. They get inside each other and produce a different kind of cell. You see the bacteria here around that cell are very, very small. And that cell in the middle, which is a eukaryotic cell, is the cell that makes proper life that we can see without the aid of a microscope. Before that, all the life on Earth, at this point, you will need a microscope to see it. So we have here what is some astrobiologists, some people into the origin and evolution of life, call it the eukaryotic revolution, because these are the cells that are able to produce multicellular organisms. And in this paradise, and you have to put the eukaryotic cell here. That is the eukaryotic cell. I'm going to fix it here. Again, this miracle didn't happen. We have the paradise here, but it didn't happen for another 1,500 million years. So that's how difficult things are. So in our paradise, we have now evidence for fossils, soft body fossils that are more than 500, 600 million years old. And we keep going to see the bottom of the ocean that was developing in this paradise with these eukaryotic cells, but not for very long. I mean, you may have collected fossils in the south coast of England. This is one of them, an ammonite from the Natural History Museum. Everything was very fine until we have these massive extinctions of life. An asteroid or whatever it was, I mean, it could have been massive volcanic eruptions, came about 256 million years ago and wiped out, as you see here in the image, it wiped out the 96% of life on Earth, almost sterilized our planet. And I have to emphasize, this was by chance. By chance. We remove any of these events from the history of the Earth, nothing that we see today will be here. Something else will be, but not that. From that extinction, we have the formation of the large vertebrates, of course, very famously the dinosaurs. And I put the ammonite here on our timeline there. The ammonite, hang on. And then the dinosaurs. I have a dinosaur here to put here at the end of the timeline. And as you probably know, and now we know it was a meteorite, it was a small asteroid actually that collided with the Earth 65 million years ago, and then wiped out 3/4 of life on Earth, just over 3/4. By chance. Let's put that in our bottom of our list of conditions. So that's where we come from. This is where mammals finally had a chance after the extinction of dinosaurs. Mammals have the chance to develop, and then we have the origin of humankind. Well, only the first humanoids, probably a couple of million years ago, but proper Homo sapiens came to be about 200,000 years, which is a couple of tenths of a millimeter in our timeline. So I don't know, Olivier, we can see this image here. So that is the origin of humankind, and this is today. I chose Einstein there. I don't know if you have Einstein coming in the next image, because the distance between these two images is the thickness of this piece of paper. I don't know if you can see what I'm doing there. So you have the origin of Homo sapiens, this is today, and the distance between these two images will be a couple of 100,000 years, which is 0.2 millimeters in our timeline. So I have to put this way. So this is the history of the universe, and this is humanity there. There is no more dramatic demonstration of humility, but you have to realize that we have achieved so much in that amount of time. So this is where we are. The most complex machine in the universe, as far as we can tell. It's just a little bit more complex than some of the mammals, like horses or elephants or whales or cetaceans. And it's a collection of hundreds of thousands of millions of cells that we call neurons, extremely complex. So the intelligence is a result of complexity, and that complexity comes from diversity. We have a diversity, enormous diversity in our rainforests, and this is a lovely painting from my country, Mexico, where we have this diversity. So that diversity is what brings the complexity that will bring intelligence. All these conditions, I sustain, are necessary. Charles Darwin made his tree of life, a very iconic image that we have in our mugs and t-shirts, and it's a very famous image, but this is the modern one. This is the modern one. That's where we are. Most of the tree that you see there on the bottom right to the right is microscopic. The plants and animals are at the top, and we occupy a little twig at the top of that tree. Another enormous sense of humility for us. Now, we are going to go elsewhere and find life. We need to go to Mars, for example, and Mars is completely dead. We have evidence of liquid water flowing on the surface of Mars, and no doubt astronauts that will be walking on Mars in the next few decades will certainly explore these dead riverbeds, digging for evidence for life, but not that kind of life that we see in the next image, but it will be more or less like a kind of microscopic fossil of a bacterium. It's not exactly the princess of Mars that we see in some of the science fiction novels, but it will be a little fossil bacterium there. That will be the kind of life that we're going to find. We have to go elsewhere, a little bit further away, to one of the moons of Jupiter that we see here going around Jupiter, the moons that Galileo discovered with his telescope. One of them is called Europa, and Europa is a frozen world. It is tiny, it is much smaller than our own moon, but now we know, thanks to the space missions, that little moon that we see here to the same scale as the Earth, you see the ocean on Europa. That ocean of Europa is 100 kilometers deep. 100 kilometers deep. There is more water in Europa than all the oceans, rivers, lakes that we have here on Earth. There is more water there, which is good news, because there is plenty of water elsewhere, and water is very important for the development of things like this, like the bacteria that we saw before. Now, we have to go further away. We have to go to the stars. We go to the stars, and we have now the technology to detect planets around other stars. We have, a few years ago, we had the front pages with artistic representations of planets going on in the research. We have modern technology. This is a very old picture because it shows the positions of planets in each of these circles. There is a solar system there. Today, we know that you go tonight, you go to the sky, look at the sky. Every single star that you will see in the sky, you can be almost sure that has planets around it. That's the kind of discoveries that we have. Here we have a collection of a lot of radio telescopes in the Atacama Desert in Chile, South America, and they have made discoveries like this. We have seen the images I showed you before of solar systems information. Well, when they saw images like this, they thought that they were artistic representations. These are real images. When you see the dark rings surrounding the star, which is in the center, those dark rings are the result of the accumulation of material that has been, so to speak, vacuum cleaned by the formation of planets. So inside of each of these dark rings, there will be a planet. And there are so many pictures like this of different solar systems information all over the place. So I have to bring you the image that we showed before when we were talking about Nicholas Copernicus. And what I'm going to show you now, it is the real thing. This is a solar system. In this case, we have to mask the central star, which is behind that little dot in the center marks the position of the star. We have to mask it so we don't get the glare of the star and we can see these planets going around the star. Isn't that amazing that we can do that? And we have the technology to do that. I find it extremely amazing. Now, will we have aliens in these planets? We have aliens. We have aliens. Where are they? We have now evidence for planets. As I said, every single star that you see in the sky may have planets. This is the Kepler mission that was looking at the Milky Way galaxy. This is a lovely picture that I took from the Atacama Desert some years ago. In this picture, you have hundreds of thousands of millions of stars. Let me say it again. Hundreds of thousands of millions of stars. Each of them may have planets around it. So how many planets are there? And this is only one galaxy. There are many more. So you see what we are doing here. We are coming to the thoughts of Giordano Bruno, who said an innumerable number of worlds of the same kind as our own. So now we are going to come to the conclusion of our talk when we have the list of conditions, including the accidental, non-biological accidental global extinctions at the bottom. So when you put all these conditions together, what do? Are you going to put probabilities there to see how much, how probable it is to have a planet which is at the right distance from the star, how much it is to have a planet that will have our moon, will have water, oxygen in the atmosphere, plate tectonics, magnetic fields, all these conditions. So if we put numbers, yes, this may be controversial. You will send us some questions about this and say, how come? I mean, 1 in 1,000. How come 1 in 1,000,000? But these are more or less educated guesses of what these possibilities are when you have solar systems. So in order to have another Earth, if we multiply all these numbers together, we will have to have an enormous number of solar systems in order to have enough statistical base to say that there will be another planet similar to the Earth, or the same as the Earth. Our galaxy has 200,000, well, more or less 200,000 million stars, and from the images taken from the Space Telescope, we can tell that there are as many galaxies in the known universe. There are 200,000 million galaxies, each of them with 200,000 million stars. So you have 200,000 million galaxies times 200,000 million stars. We get that, okay? An enormous amount of stars. You know what? The universe is not big enough. I mean, at that level of 200,000 million galaxies, is not big enough to reach another solar system with a planet where, let alone intelligence, I mean, where life can develop to the level of complexity that we have here. So we need 250 universes to get another Earth. This is very speculative, I agree. We can argue about it, but it gives you an idea, because you may say, where are the aliens? Where are the aliens? That's our position in our Milky Way galaxy. We have no evidence of them. And if you see the amount of solar systems that preceded us, there will be plenty of evidence if they were there. They will have populated our history, will be full of aliens coming from all different directions, from all different times. So now the conclusion is very important. We know the future of the sun that we see beautifully here over Stonehenge is going to change. In a few thousand million years, the sun is going to run out of fuel. It will become a red giant star. And literally, the sun will be here. The Earth will be inside the sun. That will be the end of the Earth. That will be the end of the solar system as we know it. And the solar system will come one of those clouds that we see before, because that process of recycling will continue. And our solar system will look like this, where that cloud that you see there contains the planets, and the people and the whatever we have today will be part of that expanding cloud, which is the result of the death of the sun in 3,000, 4,000, 5,000 million years to come. So we have to do something. We have to move away, as the aliens should have done. There's no evidence they did, but we have to do that because our planet is not forever. So in the process of looking at the stars here, we are now exploring space in a beautiful way. We have images from the space shuttle, originally landing from space station, but eventually we have to build space colonies. That wheel that you see there will be about 2 kilometers in diameter. Some of them will be 20 kilometers in diameter. They could carry, you see, inside the inner tube of that wheel, you have that wheel is spinning because you have to create your gravity by centrifugal action. And inside you are going to live in the bottom here, we have your atmosphere, and there will be a couple of million people living there, traveling into interstellar space, going to colonize the rest of the galaxy. Science fiction, but still probably, and it has to happen because otherwise we will die with our solar system, as probably all the aliens did before. I'm going to keep quiet now. I'm going to show you a lovely sequence of images to end the presentation. But before that, we keep this, the image just like that, because I'm going to show you this. I want to show you this. Olivier, I know you want to show this to the audience. What we have here is a scale model of our Earth, which is about 30 million times smaller. It's a lovely representation of the physical Earth. At that scale, Mount Everest here between India and China will be 1/4 millimeter high. 1/4 millimeter. That's the scale we have here. The space station, as we call it, the space station, will be 3 millimeters high. That's what the space station is, going around the Earth every 1.5 hours. And for me, the dramatic representation, well, the atmosphere of the Earth will be less than 1 millimeter thick. That's the Earth that we have. I'm making a point about the fragility of our environment. And if we talk about the oceans, if I have a piece of paper here, the thickness of that piece of paper will show the depth of the oceans. The depth of the oceans. It's only a few kilometers deep. We call it, I mean, we have 3/4 of the surface of the Earth is covered by water. There's not that much water. It's very easy to spoil it. And let me now show you a demonstration which I have seen many times. And it is very important to remember this. Look, I'm going to have this demonstration now. This is about a couple of 2 or 3 cubic centimeters of water. I put it there. So I'm going to do something here, because here on my right hand, at this scale, I have all the water on all the rivers and lakes and oceans on Earth. So this is all the water on the surface of the Earth. There is no more. And there will not be more. That's it. That's all the water that we have. Our sense of responsibility as living beings on this universe is enormous. There is no evidence for aliens. Is that evidence for absence? Probably for me, it is evidence for absence. The absence of evidence is evidence for absence. The responsibility that we have as a thinking species that has come to this planet by chance, by accident. And look what we are doing. It is ridiculous. We have to think in terms of this in order to become the aliens that are going to go and colonize our galaxy, because there are no more aliens to do that. If we kill ourselves, if we kill our environment, which is killing ourselves as well, we destroy that possibility for the future. So now we're going to show these images here. Thank you very much for your attention.
Question? Can I ask a question from the online audience?
It is time to answer your questions or to deal with them. So we have here Joe, who is relaying the questions. I will repeat the question, but he's going to read me a question now.
So this is from Malgorzata Hardy.
From Malgorzata Hardy, yes.
She's in London. She wants to know your view on what would be the most profound impact on humanity of knowing that we are not alone in the universe. And secondly, would it still be worth knowing if an encounter with the aliens might be dangerous for us and result in bad consequences? For example, Earth being destroyed or enslaved.
Yes, that last thought was made by Stephen Hawking, actually, that he will say we shouldn't advertise our presence because they will come and destroy us and steal our resources. But you know, there are aliens and aliens. There will be some aliens that may do that, others not. There are trillions and trillions of possibilities of aliens coming from all directions, from all times. There is zero evidence. So I think that possibility is extremely low. And to have within those possibilities the one that is going to come and steal our water and our oil or lithium or whatever is the material. Yes, it is very, very unlikely. But yes, the first part of the question is the impact that we have. Yes, I can imagine this sense of solitude, this sense of isolation, this sense that we are alone. I will be happy to find flying saucers and to find UFOs and all that kind of stuff, as some people very easily can detect. We spend hours and hours taking pictures of the sky. We have never seen anything, but I wish we could. But the fact that we may be alone in the universe, it is a double side. I mean, yes, it could be depressing, could be an isolation, but also gives us the important responsibility of carrying the torch of the DNA that started here. That fire is like the Olympic fire that started here almost 4,000 million years ago. It hasn't been extinguished despite of all the massive extinctions that we have, and all life that we have on Earth right now carries that fire, including ourselves. Our responsibility is to carry on and to colonize and become the aliens ourselves, the aliens that colonize our galaxy in the thousands of years to come, if we survive our own destruction, of course. There is a question from Allah here, yes?
Yes, it might be sensitive one. I mean, I enjoyed first of all the lecture, but all what you've said in tonight's event, what does that mean from religion perspective about the accidental event of the creation of the earth and the universe in general?
Well, the question has to do with religion, about the accidental situations that happen. And my answer is that everything, absolutely everything, given some rules, of course, but events happen by accident. If you realize, I'll give you a few examples. If we remove Napoleon from history, nobody, at least in Europe, will be alive today. It will be other people, the people that met your parents, your grandparents, they wouldn't be there. They will be grandparents of other people. Instead of us, will be someone else. If we remove Hitler, if we remove big events, big wars, and all these kind of things, this pandemic is changing the future because a lot of people are going to be born, and a lot of people are not going to be born, depending on which way you do it. But it's just by chance. If that asteroid didn't hit, the dinosaurs will still be here. In 200 million years, they never developed intelligence. So as far as we know, they will be still the same. So everything is by chance. And there is no way of saying there is a kind of supernatural force there, which I find it fascinating, really, magical and beautiful, really, that it is by accident, and gives us the important responsibility that we are here because as a consequence of those accidents. It is extremely important. It's an enormous degree of responsibility. So we have to change the way we live. We have to change, and this pandemic plague is really making us change, or some of us at least. I mean, a lot of people, especially the big powers, are just waiting to keep going with the same greed, exploiting and destroying the rainforest and killing people. Who cares? The important thing is the economy. The economy? Hang on. What? Are you going to destroy the rainforest for the economy? Are you going to kill people for the economy? Then you have no people, you have no rainforest, and you have your economy. To do what? I mean, it's ridiculous. We have to change. We have to find a way of economy that doesn't feed from the environment, doesn't feed from people, but on the contrary, is the environment and the people who feed the economy. So people are at the top, the economy is feeding that, and it's the other way around.
I have a couple of other questions.
Another question, yeah?
Some more questions from our online audience. This is from Jatin Desal. As we can't travel faster than light and the distances are so vast that it will not be surprising to never meet aliens?
Well, yes, there is what is called the filters. This is the most important one. If we don't see aliens, it's because there is a fundamental limitation that doesn't matter how much millions of years you have to develop your technology. You will never overcome this major restriction, which is the speed of light. You cannot travel faster than light. Therefore, wherever you go, even in our galaxy, it will take you thousands or tens of thousands of years, even at the speed of light. And therefore, it will be very difficult to do that. But even so, I sustain that a civilization that was here in our galaxy, say 2,000 million years ago, which is very probable, would have done that. Because little by little, you can, not in a single trip, but you can go and colonize the galaxy. But that could be a possibility, yes. But I insist, we have to remember all that list of conditions that we have. That list of conditions is extremely important. We are talking about winning the lottery once, and then again, and then again, and then again. The eukaryotic revolution from bacteria to the eukaryotic cell, again, is a very improbable event. It's a revolution, it's a miracle. Will that happen in other places?
Thank you. And here's another question. You may need to repeat the question. I'm not sure everyone can hear me. So this is from Tony Hart. Thank you for such an interesting lecture. Do you think humans are likely to destroy our planet before it gets destroyed naturally?
Do I think that the humans will destroy our planet before it is destroyed naturally? The answer is a rotund yes.
That's quick.
Yes.
Okay.
We are able to do that, but I have to say, we have to define what the planet is, because what we call the planet is our environment. It is a couple of tenths of a millimeters deep in the oceans and a millimeter high in the atmosphere. It's not that much. It's not the planet. It's a little thing here. And our planet, I think, has survived massive extinctions, which are hopefully more powerful than the one that we can produce. So I think one way or another, our planet will survive.
And here's another one from Malgarzata. If we had to pass on and die out as a civilization and a species, and we had an opportunity to pass on one message to a future alien civilization, what do you think this message should be?
Well, yes, the question is about a message to future alien civilizations. It's a kind of a time capsule, I suppose. Is that what you mean, Malgorzata? Is the time capsule that we have a message that we were here and we made a mistake or something and we destroy our planet and then don't do it, and then that kind of stuff. It will be a kind of message. We have to remember that there are 4 spacecraft, the 2 Voyagers and the 2 Pioneers, that are already on the way to the stars, and they have some messages about who we are and where we come from, although it doesn't show that we are destroying our environment. When these spacecraft were sent in the 1970s, the environmental issues were not that drastic as they are today. But that will be the kind of message.
And here's a question from Jose Prieto. If aliens are 1 million years more advanced, they may be impossible to detect because of their superior technology.
Again, we have aliens. The question is about aliens that have so much superior technology, which is so superior to us that we will not recognize them. And I have to insist, there are aliens and aliens. If there is another civilization of aliens, there will be millions. It's not only 2. There will be millions. Some of them will be more advanced. Of course, if we have evidence for them, they will be more advanced than us, and we will know about them. And one thing I have to say, any life in the universe, from my perspective, and there are arguments here, but it has to be complex, and it has to be based in complex chemistry, and the chemical element that produces complex chemistry is carbon. And the carbon produces components which are in the gas form, in those clouds that we saw, the interstellar clouds out of which the stars and planets are formed. And being in gas form is able to combine and to produce more complex molecules. Only carbon can do that. And it's extremely versatile element. So any life should be carbon, and it will be very similar to what we have here. But you may say, well, how about robots? How about alien spacecraft that come? Well, if that was the case, we will have evidence. I mean, we have 4,500 million years of history on Earth with records on rocks that will show evidence. I mean, unequivocal evidence of presence of alien artifacts. There is 0.
And a final question from Joanna Sulek. If we can't communicate with the aliens, practically speaking, isn't it the same as being alone, as we would never meet? And she also thanks you for your interesting thoughts.
Yes, the question is very important, Joanna. It is the lack of communication because of the problem of not having the technology that can overcome these enormous distances. Yes, and we come to the point that we don't know if the aliens are there or not. They are not here, therefore none of them, thousands of millions, could come to see us in this amount of time So either they couldn't do it, none of them couldn't do it because of limitations, or simply they are not there. But I agree with you, Joanna. Either way, it is quite depressing in a way. But again, we are here, and we can do it, and we should survive as a species, and we keep our environment, and then really survive. Go to space, not as a nation, not as a company, not as an industry, but as humanity, as a whole. The first plaque left by Apollo 11 on the moon said, "We came in peace for all mankind." So we have to go in peace for all mankind as a single human race to explore space. Because when we do that, we are going to make sure that the conditions here on Earth will be far better. We will have a sustainable environment, we will have more equality in our fellow citizens, and we will have much less problems that are plaguing now. If we are going the same way that we have colonized America, the continent, not the country, America is a continent, the same way that America was discovered by Columbus and then colonized and destroyed, we know what happened there. Are we going to do the same thing with the same attitude? Are we going to export that attitude to space? We have to fight against that. We have to fix this thing and learn how to live together, learn how to be sustainable, then go to space and export that instead of what we are exporting now.
And the other comments were just thanking you for your interesting lecture.
It is a pleasure. Thank you very much for your questions, and it is a pleasure to have done this.
Thanks.
Thank you. Thank you very much.